In this problem, we will prove that the product f0 times f1 times f2 until fn is equal to fn plus 1 minus 2, where fn is the Fermat number 2 to the power 2 to the power of n plus 1. Of course, we will do it by induction, but at first we will prove this equality, which will help us in our work. Fn plus 1 minus 2 is equal to Fn times Fn minus 2. So let's just start. We have Fn plus 1 minus 2 is equal to, here Fn plus 1 is 2 to the power 2 to the power n plus 1, Fn plus 1 plus 1, this is Fn plus 1 minus 2, It's of course equal to 2 to the power 2 to the power n plus 1, and plus 1 minus 2 is minus 1. It's equal to, here, 2 to the power 2 to the power n plus 1 is 2 to the power 2 to the power of n times 2 minus 1. And we know that a to the power n times m is equal to a to the power n to the power of m. So here it's equal to 2 to the power 2 to the power of n squared, using our rule, minus 1. But 1 is 1 squared, and this is the difference of two squares. And we know that it's a special product. It's equal to 2 to the power 2 to the power of n plus 1 times 2 to the power 2 to the power of n minus 1, which is equal to 2 to the power 2 to the power of n plus 1 is just Fn times, and this number is 2 to the power 2 to the power of n minus 1 is plus 1 minus 2. And here you see this number is just Fn. So it's equal to Fn times Fn minus 2. And we have gained our equality. Now back to our product, which we will prove by induction. So let's start with the base case. With the base case, n of course equals 0. So in this side we will just have f0, and in this side n equals 0 we will have f1, 0 plus 1, minus 2. So f0 here, 2 to the power 2 to the power of 0, which is 2 to the power of 0 is 1, 2 to the power of 1, which is 2, and 2 plus 1 is just 3. F1 is equal to 2 to the power 2 to the power of 1, and 2 to the power of 1 is 2, 2 to the power of 2 is 4, 4 plus 1 is 5, 1 minus 2. And of course you see we have 3 equals 5 minus 2, meaning that our equality holds, and so the base case n equals 0 holds. Now let's prove the inductive step, meaning that we will prove that f0 times f1 times f2 until fn is equal to fn plus 1 minus 2 implies f0 times f1 times f2 until fn plus 1 is equal to fn plus 2 minus 2. This is the inductive step. Now we have fn plus 2 minus 2 is equal to, and now we will use our equality here. If n plus 2 minus 2 with n plus 1 here is equal to fn plus 1. So our n is equal to n plus 1 here times fn plus 1 minus 2. But fn plus 1 minus 2 with our inductive hypothesis is equal to here fn plus 1, and we replace fn plus 1 minus 2 with f0 times f1 times until fn, which is of course equal to, this term is equal to f0 times f1, just rearranging, times f2 until fn, of course, times fn plus 1. Now we have gained our inductive step. And from here, we can say that for every non-negative integer n, we have f0 times f1 times f2 until fn is equal to fn plus 1 minus 2. And this, of course, concludes our problem.